Okay, so vanilla SGD. So we take an estimate of the gradient based on a batch, right? This is an average over the batch of the gradient of the loss with respect to the batch, with respect to that batch element. There's a true gradient, which is the expectation over the population, or maybe take that to be the whole training set. This is just a batch. This is the whole training set. There's a full gradient, which is the average over all the training data of the loss gradient. And here, this eta is a learning rate. So what are the issues? One is the gradient estimation, right? Because we're looking at a batch, we're looking at a little subset of the data. This gradient estimate is not the true gradient, right? It's some noisy approximation, some average of a small set. A second issue is that as the parameters change, as you're doing SGD, the parameters are changing. And as the parameters are changing, the direction of the gradient is changing, right? So I'm calling that gradient drift. And what we're going to think about is convergence, right? What we want to do is get this gradient descent to find an optimum of the loss, right? And an optimum of the loss is a point where the gradient is 0. So we're looking for convergence, meaning we want to converge to what's called a stationary point. A stationary point is a point where the gradient is 0. It's not necessarily a global optimum. It might even be a saddle point, although that doesn't happen in practice. Okay, so that's convergence. Another issue is exploration. So I'm going to argue that we want to think of stochastic gradient descent as being very similar to MCMC. So if you've seen Monte Carlo Markov chain simulation, what we want to think about, the way we want to think about stochastic gradient descent is that this sampling of the gradient based on a small sample has noise, right? It's a stochastic estimate of the gradient. And when we start making these moves with stochastic estimates of the gradient, we've introduced noise into the SGD process. Okay, so the SGD process becomes noisy. And in MCMC, there's this notion of temperature, which I'm going to be coming back to and talking about a lot in SGD. The idea is that this noise can actually have a good effect, right? Because it can do something like simulated annealing. It can cause us to walk through the space of parameter values with a bias towards lower energy, but still noisy, so it jumps out of local minima. So there's an analogy between stochastic gradient descent and MCMC. And I'm going to be talking about that a lot. So here's a simple example. Suppose I just want to estimate, suppose I've got a loss function, one parameter in my model, which I'm going to call beta. Think of beta as the model parameter. And I want to tune beta to minimize the average of the loss, right? And the average of the loss is an average over y drawn from the population of this squared difference between beta and y. And what's happening here is that the minimum of this is just the average y. Right, the minimum of the value of beta that minimizes the expectation of this squared difference is just the average value of y, the mean of y. So if I apply the gradient descent analysis, the gradient is the gradient with respect to beta of this average loss is just you just differentiate this and you get beta minus twice the expectation of this. So the point where the gradient is 0 is just the expectation. Now, if I have a finite batch, this is just an example. If I have a finite batch, then this estimate of the gradient is beta minus the average value of y over that batch, which is not going to be the true mean, right? So what's happening is we get noise from g hat. Okay, so now the classical convergence theorem. So in the classical convergence theorem, what we're going to do is we're going to have this learning rate be a function of time. So as we're running SGD, the learning rate is going to be getting smaller. And there's a classical convergence theorem for any sufficiently smooth non-negative loss. If the learning rates are all positive and the learning rate is going to 0, but the sum of the learning rates is going to infinity. So how could that be, right? I could take, if I took 1 over the square root of t, it's going to 0, but the integral is the square root of t, which goes to infinity. Right, that's the standard example. So the learning rate's going to 0. The sum of all of the learning rates is going to infinity, but in the classical theorem, you require that the sum of the learning rates squared is finite. Okay, and then we have this theorem that under these conditions, what happens is that stochastic gradient descent will converge over infinite time to a stationary point. Now that's a little bit misleading because there are technicalities that you can construct examples where it converges to a limit cycle. Weird things like that. But there will still be a limit. Any point on that limit cycle is a limit point of the cycle. So but anyway, the right way to think about this is it will converge. It can also, the parameter space can also diverge. If the optimal has a probability 1 in it, a softmax can never produce a probability 1, right? Because a softmax has a finite probability for all possibilities. So it's possible that the temperature, if you have a temperature parameter, the temperature will diverge, or the beta parameter could diverge to infinity. Okay, so now stop me if there are any questions. I love questions. Now I'm going to try to prove this. But this is a physicist proof. So for me, what a physicist proof means is that it convinces me, but it's not rigorous. Okay, so how do we think about this? What's going on here? The learning rate is going to 0. So that means if I wait long enough, the learning rate is getting arbitrarily small. So if the learning rate is getting arbitrarily small, then it's going to take an arbitrarily large number of updates to change the parameters. Right? So if it's going to take an arbitrarily long time to change the parameters, that means that we're getting an average over an arbitrarily large number of stochastic estimates of the gradient. Now, since the sum of the learning rates is going to infinity, no matter how long I wait and how small that learning rate has become, there's an infinite amount of oomph left. Oomph. Each update has an oomph sort of proportional to its learning rate, right? So but the sum of the learning rates goes to infinity. So I've got an infinite amount of learning rate size left, no matter how small the learning rate gets. So eventually I'm following the true gradient. And as long as I follow the true gradient, that true gradient will take me to a stationary point. And now in that argument, I never used this condition. And I'm not really convinced that condition is necessary, but it's based on my physicist's argument. Yeah.
Here for like sufficiency mode, like I was talking about it in the sense of like else mode function.
I forget exactly. So there's a reference here to the actual proof. You can find it in neurodynamic programming, Bertsikis and Tsitsiklis, and I forget exactly what smoothness. Probably second order. You want second order smoothness. So second order Lipschitz. So a stationary point might be a saddle point. You know, you get these, it's positively curved this way and negatively curved that way, but right at the saddle point, there's no gradient. Is that making sense? Imagine a saddle on a horse, right? Right in the middle of that saddle on the horse, it's perfectly horizontal, but you can go down or you can go up. So it's not a local minimum. Also, in principle, you could have a local maximum, which would also have a stationary, also be stationary at the top. Okay. SGD is a form of MCMC. So here's the learning rate as temperature. So I'm going to be talking a lot about temperature. And when I've given this class before, and I start talking about temperature, it's not clear why I'm using that word or what I mean by it. So I'm going to think just intuitively it's just an empirical fact that if I run at a certain learning rate, my loss, if you look at your loss on your training data or your validation data, the loss will drop because you're doing stochastic gradient descent, and then it will converge. You'll reach some kind of stable loss. So what in this picture we're seeing is the blue curve here is a standard. That would be a standard plot of the loss over time at a first learning rate and then at a second learning rate. Typically, you drop the learning rate by a factor of 2. So when you drop the learning rate, intuitively there's less noise, right? Because the learning rate is putting more weight on each step. And I in that previous argument, I said as the learning rate is close to 0, you're effectively averaging more batches before in making in making the parameter space, the parameters move a certain distance. So when you drop the learning rate, the noise is reduced, and this drops. So think of temperature. Think of this as being like MCMC. And in MCMC, there's a temperature parameter, which is adjusting the amount of noise in your stochastic moves. And as you drop the temperature, the MCMC energy, you make this analogy between loss and energy, drops. So I'm going to make this a lot more technical, probably next lecture, actually sort of try to establish a formal, rigorous relationship between the learning rate and the temperature. Question?
When we talk about converge, numerically, like what's the kind of formal definition we can use? Because like you can look at it and by like glancing at it, you can say, oh, that's converged, but it depends a lot on, I think it depends on the magnitude of your error and lots of other things. Like you set a threshold for variance and loss.
As far as I know, when people say converged in the deep community, they're mainly talking about looking at it and saying, oh, it looks, like something weird happened right here in the blue, right?
Like, how did they just decide that they were going to drop the learning rate at 150 ethics and not at 100? Like, that was similar to me.
So I haven't said what the red here is. So this was a paper from iClear 2017, and what they did is they run very cold, right? So they run right down here right away. And there's a conventional wisdom that if you do that, you'll converge. If you initialize it with a very small learning rate, you very quickly drop down much lower than if you're running at the higher learning rate. But typically the performance of that point is not as good as if you let it run out here and then drop it. Because the idea is that this does more exploration. But here what they're doing is they're dropping it, they're recording the parameter value there, then they're increasing it back up to here, then dropping again, recording the parameter value there, and they're getting us so that we'll later in the class we'll talk about the value of ensembling models. You take a bunch of models and you vote them rather than looking at one model. So this paper was about building an ensemble efficiently by raising and lowering the learning rate. But but the point I want to make is that you can see these optimum getting better over time, and you can see the sort of dramatic effect of the learning rate. You know, you can raise it, it'll fly back up here, and then lower it, you'll fly back down here, and you can do that repeatedly. In MCMC, that's called tempering, raising and lowering the temperature. Uh-oh.
Follow, sorry, so when we're looking at the blue lines, really, like, if, say this takes a week to run, so they can't monitor and decide on the fly when to drop the learning rate. They have to programmatically decide the way to do that. But a priori, they don't know that, like, the magnitude of the drop in learning rate over the ethics. How do they decide the threshold for definition of convergence, the trigger to actually drop the learning rate at a certain number?
So what happens is the transformer, for example, is a particularly difficult thing to train. And people spend a long time playing with it. And then you get a recipe, you know, whoever publishes the paper on the transformer will give you a recipe for those decisions. So it's just really just empirical. I'm in trouble here. Something's wrong with my laptop. Oh, wait a minute. Here we go. There we go. So that when the learning rate is high and the loss is high, that's when you're doing exploration. Both curves had regions of high and low learning rate. Okay, now what I want to do, now what I'm going to do is focus on temperature. And the idea is that temperature is the really important hyperparameter. Right? Your hyperparameters are things that are parameters of your learning algorithm, not parameters in your model. Now, there are other hyperparameters. And the first thing I'm going to talk about is batch size. And what I'm going to try to do is analyze the interaction between batch size and temperature. And this is something that I was shocked when I learned that that this convention for a batch was to average over the batch. Your estimate of the gradient is the average over the batch. That convention couples the batch size to the learning rate, couples the batch size to the temperature. It makes and what you would like to do is have a temperature parameter that's not coupled to the batch size and not coupled to the momentum parameter either.
Just for clarification, I'm using learning rate and temperature as a change rate because I'm not entirely sure I understand why.
Yeah, so by temperature, I want to mean when you run your SGD with whatever your hyperparameters are, you converge to some loss. And I want to think of that loss value as defining temperature. And so the idea is that we want to have, and the idea is that running SGD under various hyperparameters. I'm going to be talking about the batch size and something called momentum. That if you introduce these batch size and momentum hyperparameters in addition to the learning rate, what's really important is the temperature and the temperature schedule. And you want to understand how to predict what the temperature is. So in vanilla SGD, if you're just running vanilla SGD with just the learning rate and batch size 1, I claim the temperature is determined by the learning rate. That as you reduce the learning rate, that loss value is going to go down. Did that help? A little bit.
So after this, the final loss that you reach after
That you converge to, right?
and then so the lower, the hotter the temperature. You were saying the other one, like the one where like it dropped really quickly. You were saying that was running cold, and that was pretty high loss. So I guess it's like, is it higher the temperature, the lower the converged loss? Like higher the temperature, higher the converged loss.
The higher the temperature, the higher the converged loss.
Okay.
Each one of those curves, so there was a series of things like this. Each one of those curves went hot, cold, hot, cold. And cold is lower learning rate. Okay, so this is what I just said. So this is just a picture. This is from the original ResNet paper. This is just a picture of a typical learning rate loss schedule. So here we're running at a higher learning rate. We drop the learning rate. We converge at the new learning rate. Then we drop it by a factor of 2. And this is from the ResNet paper. The little squiggly lines are the training loss, and the solid lines are the validation loss, like the generalization loss. And this is 2 versions of the network. But the point I want to make on this slide is just that as you're training, you run at one temperature, then you drop the learning rate, then you run at another temperature, then you drop the learning rate, and you run at another temperature. Sorry? I still didn't hear. One is the one. Oh yeah, in the picture, you have thin lines and thick lines. The red and the blue are 2 different networks. One's 18 layers and one is 34 layers. And the thin line is the training loss. So the training loss is noisier than the generalization. So the generalization loss is you have some validation holdout set that you're not training on. So you train on the training set and you measure your validation loss. And that's the validation loss is the thick line. I don't think so. Well, it's certainly true in this picture. I guess I could try to make something up. The algorithm is looking at the training data, right? So it's fitting little pieces of the training data, and presumably it fits different pieces of it better over time. Whereas it's not looking at the validation data at all. So the validation data is a more stable test. I don't know, but I just made that up. Batch size and temperature. So when I very first taught, I told you this already, when I very first taught this course, I was shocked there was this 1 over B here, that it was taking an average. Increasing the batch size under this convention decreases the noise in the gradient, right? The batch, that gradient estimate gets better as you have more data points that you're averaging. So a better estimate of the gradient is not as noisy, right? So you're gonna run colder because you've got better estimates, right? There's less noise in the system. And if temperature is the main thing governing the success and process of your SGD, you need to know that your batch size is coupled to your temperature. If you double your batch size, you're getting colder. So we can make the temperature independent of batch size simply by, so when I first taught this course, I said, no, you shouldn't take the average, you should just sum. And the intuition is that if we're running at a modest learning rate, the parameters aren't really moving. Right, so consider running at batch size 1. So we're only taking one example. And what these equations are supposed to show, if you're running at batch size 1, you're only taking one example. If your parameters aren't changing, then as I run at batch size 1, it's and I do B steps, capital B steps at batch size 1. That's what these equations are saying. I do capital B steps at batch size 1. And each time I do an update, I'm using a slightly different parameter value. But it's only slightly different, right? So it's almost the same. If I do B steps of batch size 1, it's almost the same as doing batch size B without averaging, right? It's the same as doing B update, just taking all of those updates and adding them together. So if eta, so it's sort of equivalent to this, right? So if this is the optimal learning rate at batch size 0, at batch size 1, this should be the optimal learning rate at batch size B if G hat is defined to be the average, because this B will cancel the 1 over B in the definition of G hat. And there was this big development. This paper was a big development. They were running ImageNet. People were, ImageNet was the standard benchmark for image classification. And it took weeks and weeks to train an ImageNet model. And this paper demonstrated that you could take the batch size to be huge. Right? If you run the batch size in parallel, you put your model over 100 machines, compute a huge batch and do one update over a huge batch, you could get that to work. And because of the parallelism, now you can train in an hour instead of weeks. But there's this coupling between the batch size and the learning rate. So one of the things they had to do was, take the learning rate to be the batch size times some base, size 1 learning rate. The learning rate had to be scaled proportional to the batch size. So it's empirical validation of the argument I just made. I just did. It was obvious. I don't know. It felt obvious to me that this made sense, at least for some size, for some scaling of the batch, by that argument that's on this slide.
Would that suggest using a larger batch would converge to a higher loss? Previously we talked about larger versus higher.
Well, the idea is that if the batch is large, and you're taking an average over the batch, and you're taking that to be your gradient estimate, that because you're averaging over the batch, that gradient estimate becomes more accurate as the batch size gets larger. And because it's more accurate, it means there's less noise. And if there's less noise, you're running at a lower temperature.
Yes, but I guess I just don't understand the coupling between batch and the learning rate, because when we were thinking the equivalent learning rate would be much larger if we on batch size without changing the because you have the equation like learning rate equals to initial learning rate multiplied by the batch.
So let's start with this equation, right? So the estimate of the gradient, you go to PyTorch, your estimate of the gradient is going to be this given by this formula. And this is still true in PyTorch. And in PyTorch, you'll take that, PyTorch will if you look at this last line here, PyTorch doesn't do this, right? It just takes your learning rate times this estimate. And the question is, and my claim is if I hold the learning rate constant and increase the batch size, things are going to get less noisy and you're going to be running colder. And the argument is that if there's a learning rate that's optimal for batch size 1, call that eta 0, that if you want to run at the temperature corresponding to eta 0, then what you can do is just say, well, taking the update over the batch is very much like taking batch size updates for each batch element. And that corresponds to multiplying eta 0 by b to cancel out this 1 over b here. Did that answer your question? Yeah. Okay. So batch size is coupled to temperature. There's another parameter called momentum. So if you have done some, taking a course in physics at some point in high school or something, you know about momentum, right? So you've got something moving, it's got momentum. And what we're going to do is say that the parameter value of our model, we're going to give it momentum. So the gradient is pushing it on a certain direction. We take a batch, we take a point, an update, that's going to push on our parameters, but the parameters also have a velocity, and that push is just going to gradually change the velocity. So the parameters have momentum. This is sometimes called heavy ball momentum, heavy ball SGD, right? And so we have these equations here. So this is the standard. If you look at momentum in PyTorch, this is what you'll see. So there's a velocity, that's the velocity at which the parameters of your model are changing. And there's a velocity update. So the velocity update multiplies the previous velocity by some decay. It's moving through sludge or something, right? So it's slowing down. So the previous velocity is decayed, and we add the learning rate times the gradient estimate, so that the gradient estimate is like a force acting on this particle, on this, okay? And then you update the parameter by the velocity. And the velocity is being influenced by so why? Yeah, why do this? There are theorems in convex optimization that rely on momentum. But those theorems are all about the second order structure of the loss surface. There's some optimal bowl and it has some, typically you draw pictures with ellipsoids about there's this local optimum. But the second order analysis, I think, and I think it's a widely held view, is controversial in deep learning. So I'm not very happy at all with the theoretical motivation that's typically given, right? So you're going to see my spin on momentum. And what I'm going to focus on is the coupling between momentum and temperature, because I'm still arguing that temperature is the fundamental thing that's governing what your SGD is doing. And I'm going to argue that this is also just a simple, I claim people get confused with momentum. They think it's helping when all it's really doing is playing with their temperature. And if they could just had a nice temperature parameter that was independent of momentum, maybe momentum doesn't do anything. This slide jumps ahead. So my claim is that if you take the momentum parameter, if you set your learning rate in PyTorch to this formula, where that's the momentum parameter and that's the batch size, you will get a stable, you'll get a stable temperature independent of the batch and the momentum. So that's where I'm going. I just wanted to put that up front. And that also has empirical support. In this paper from 2018, they do both scaling the batch size and the momentum parameter in terms of, they couple those to the learning rate in a way that's consistent with this formula. Well, one way to think about this is that this is saying that the learning rate you use, right? If you use a learning rate with no momentum and batch size 1, and you tune your, if you conceptually could tune that learning rate to perform well, whatever your performance metric is, then if you introduce B and mu, you take the learning rate that you did for the batch size 1, and by this formula, you'll get the learning rate to use that gives you the same temperature. So this is saying that the learning rate, whatever it is, scales as 1 minus mu times B. Should scale that way to get the same temperature.
So even though we drop the subscript on eta, the time subscript, we might still decrease the temperature. This is just setting.
This is just how it depends on mu and B, right? So you can still make it like this mu0 could have a time, could depend on time. Okay. What I'm going to do is analyze momentum. There's something that's much conceptually clearer to me than this momentum equation, because this momentum equation, oh sure, it looks like physics, but why? Why should looking like physics make it a good thing? So the thing that's much clearer to me is this notion of an exponential moving average, and this comes up a lot. Exponential moving averages come up a lot. So an exponential moving average, I'm gonna give an intuition, and the intuition is that an exponential moving average is analogous to a moving window average. When I run on my watch, there is my time in the last mile. Right? It takes, where I was 1 mile ago and where I am now, and it gives me my time. That's like a moving window average. It's like an average of my, my velocity over some period of time. It drives me crazy because I want to know if I'm running faster or slower, but there are times falling off the back of that window that are influencing my what it's telling me my 1 mile average is. But nonetheless, this is a useful intuition, right? If for a capital N, I could take that last mile average is analogous to taking an average of the last N data points. And I claim that this intuitively, taking an average of the last N data points, can be done more efficiently and actually more meaningfully to me by taking an exponential moving average. So I take a moving average, I define the value at time t to be 1 minus 1 over n times the value at time t minus 1 plus 1 over n times the new value. So this is a convex combination of the previous value and the current value to get the next value. Is that making sense? And the claim is that if n is large, this is like 1 minus epsilon. And if I look at, if I feed this with some initial value and then take all zeros, the effect of that initial value is decaying like e to the minus t over n. This is if I give it an initial value and then nothing, that initial value decays exponentially, right? It's getting multiplied by 1 minus 1 over n every time. And that decay after capital N steps is exactly 1 over e. So it's analogous to this capital N size moving average. Good. So this is very abstract, right? I'm saying I just consider any sequence of values xt, right? Consider any sequence of values, and x tilde is the moving average, is the exponential moving average of this sequence, where intuitively you're averaging over the most recent capital N. Now, we are going to talk about an exponential moving average of the gradient estimates, right? That's where I'm going. And the claim is that momentum is nothing other than an exponential moving average, updating with an exponential moving average of the gradients. Okay, now in previous years, there's been a little bit of confusion. If you look at PyTorch, in PyTorch, when PyTorch uses an exponential moving average, it's almost always written this way. So that just if you read Atom, or there are many places it arises, and it's generally written this way. And here beta is a number very close to 1, and 1 minus beta is a number very close to 0. So I'm going to write this way, where I think of this as a running moving average that's approximately averaging over the most recent N, capital N. In PyTorch, you'll see it written this way, where this beta parameter is typically either 0.9, 0.99, or 0.999. So this is very close to 1. In principle, it could be any real number between 0 and 1. So that's another confusion. I use capital N, but really any convex combination is valid. Beta can be anything between 0 and 1. But 0.9 would correspond to averaging over 10, 0.99 is averaging over 100, and 0.99 is averaging over the most recent 1,000. Okay. So this is the momentum parameter. This is the heavy ball momentum equation right here, right? That's the equation that you'll find for momentum in PyTorch. And I'm going to replace this parameter. This is a number near 1, right? I'm replacing that with 1 minus 1 over n. It's just a reparameterization. I'm just going to use n instead of the mu. And then I can rewrite this term as 1 over n times that term, right? And then it becomes an exponential moving average. But what is it an exponential moving average of, right? It's an exponential moving average of n times eta times g hat. That's weird. Am I making sense? So we've got this extra factor of n in there. So let's just think about what we would do, which to me is a lot more sensible, right? Which is take a moving average of the gradient. You know, what's the average of the gradient over the last n steps? And just define that, I'm going to define that to be g tilde. And that's just conceptually clearer. I know exactly what that means, right? That's a moving average, exponential moving average of the gradient. It turns out that this equation we just had, because the moving average of n eta g hat is n eta times the moving average of g hat, right? That equation that I just had can be written this way, that the velocity in the standard parameterization in PyTorch can be written this way, where this is just the moving average of g hat, of the estimate. Okay, so if we want this to be well, this is just sort of carrying that through. This is the update that we're making with this factor of n in it, where this is a moving average. Okay, now I'm going to make this rule of thumb, intuitive rule of thumb. So this is being a little physicist-y. This intuitive rule of thumb is that your temperature is going to be determined by the impact. I've got my batch. I've got all the batch elements. Pick one batch element, one example from your training data. That one example from your training data has a total impact on your parameters. Okay, that one, like the sum impact that data point has on your parameters. If I use an exponential weighted average of the gradient, that one data point is making a contribution to updates in the future, right? Because it's getting averaged into the future updates. So the question is, what's the total contribution of that data point to the parameters? And my physicist argument is that's what's going to determine temperature. What's the impact of this data point on the moving average, on the parameters over, its total eventual impact over time. And if you think about it, when it first shows up, it gets multiplied by 1 over n, right? In that exponential moving average. And then for every future point, every time we do an update, it's getting multiplied by 1 minus 1 over n. So the total number of contributions is the sum over all time of the contribution at that time, which is 1 over n times 1 minus 1 over n to the time. Am I making sense? It's this equation. The total impact is the sum of all the impacts. The sum of all the impacts is 1 over n times 1 minus 1 over n raised to the delay that happened between the initial entry and the place the update was actually made. And this sum is 1. So in an exponential moving average, the total impact of every data point, if I'm just taking an exponential moving average of the gradient, is 1. It's as if the batch size was 1. But the update equation you get multiplies by n. Right? So what you really need to do to get this to be the same temperature is to divide by n.
Why is it always something up to infinity? Like I thought it was finite sum. Like if you take the one training example, like Theorem, but it's going to have it comes with like doing a finite number of computations every time that we consider that training example. So I might misunderstanding all that equation.
You're talking about this equation?
Yeah. Like why like it end up becoming a series, but I don't understand why we are summing up to infinity.
Well, some estimate of the gradient arrives. That estimate of the gradient gets but it's contributing to this exponential moving average. So it's making a contribution to each update in the future, but that contribution is decaying exponentially, right? Because every time you make a step in time, the previous estimate gets multiplied by 1 minus 1 over n. So the impact of that data point is decaying exponentially over time. And I'm just modeling time as going on forever. But it doesn't matter because it's decaying exponentially. It's going to be essentially gone after 5n. Every time you do n, it's down by a factor of e. So it's, the effect is going to decay. Did that help? So the idea is that if we had an update in terms of the running moving average, the exponential moving average of the gradient leaves every data point having contribution 1 times eta, but the momentum equation introduces a factor of n. Which will, really affect our noise, our temperature. so I've argued that the update is already sort of dividing by b, and it's multiplying by n. So what we need to do to get this to be a stable number independent of b and n is multiply by b and divide by n. And mu, because mu is 1 minus 1 over n, you get this correction. Here. Oh, so G, this is the gradient for batch element B at time step T.
Right. And I'm asking like, what's so you're saying this is the total effect of that?
Of this one gradient,
On what? On like
the parameters. It's the effect of that on the parameters, right? Because the parameter update, this is the parameter update equation. Right, where this thing is the running average, is the exponential running average. So if we were doing batch size 1, we would look at one point in our training data, one XY pair, and we would update the parameter, right? And I'm thinking sort of causally. If I look at the parameter, so if we're running slowly, if the parameters are changing slowly, then I can think of the parameter value being used over time as basically the same parameter value. And so I can say, well, if I run for some amount of time, the parameter value over here has been updated. And how much does that update depend on this particular point measurement in time? Right, so there's a delta in that thing that's due to this one measurement. And so that's what I'm talking about. How much does this data point influence the parameters? Well, when you start using an exponential moving average of the gradients, the effect of that one data point gets spread, right? Because the moving average incorporates that data point over time. But the claim is that when you add up all those effects, it's 1. That data point is making up, with a simple exponential average, is making its total contribution is the same as it would have if we were just doing it one at a time. But because of the way momentum is parameterized in PyTorch, we're not using an exponential moving average of the gradient. We're using something that's an exponential moving average of n times the gradient. So it amplifies you're amplifying the effect of that point by n. Okay. That little section was meaningful to me because I was very upset about the PyTorch parameterization of things. And it was nice to see empirical confirmation. Okay, now we're going to talk about gradient flow. And this is going to be important when we're going to do some things with stochastic. We're about to enter a little section of this class that's probably the most mathematically challenging piece of this course. Now, I'm sure some of you are thinking, oh my God, you mean it's going to get worse? We'll see. It's not going to get worse quite yet, I don't think. Gradient flow. All right, I want to talk about gradient flow is a deterministic differential equation. And it's this differential equation right here. So this is your model parameter. And I'm going to take a differential equation. I'm just going to write this down at first. This is just a differential equation. It says that the rate of change of the model parameter over time, continuous time, is equal to the negative gradient of the loss function. And the loss function is going to be, the gradient of the loss function depends on the parameter value. Right? So this is a differential equation. Right? It has some continuous solution over time. Take the, and so this is just the definition of the gradient. Now, why is this, why am I talking about this? What does it mean? Well, suppose we were to do a numerical approximation of that differential equation. Okay, if I'm going to do a numerical approximation, I'm going to take discrete time steps, and I'm going to try to make my discrete time steps small enough that I can approximate the next value of the parameter value as the gradient times delta t. Right, the derivatives, not the gradient. My parameter is changing over time. I've got this differential equation that says it's changing at a certain rate. The rate is the gradient. So I'm just going to numerically integrate it with this equation. The change in the parameter value is minus the derivative times delta t. Okay, if you look at this, that should look a little bit familiar, right? Except that the only thing that's happened here is that delta t looks like a learning rate. Right? So what I'm arguing is that if that delta t looks like a learning rate, then then SGD, or this, I'm talking about total gradient descent now, not SGD. Let's say this is the total gradient. A total gradient update with a learning rate is just a numerical approximation of that differential equation. So it's this thing that's really interesting, but the fact that it's approximating a differential equation allows you to think about it as a differential equation. And what that means is that you can take the sum of the learning rates, right? If the learning rate is really delta t, then you can take the sum of the learning rates and think of it as time. Right? So now we've got a notion of time in our SGD. Is that making sense? So the sum of the learning rates is time. Okay, so this slide is sort of pointing out that if you think of this as a numerical process, right? If I take delta t to be small, and if I keep taking delta t smaller, then that numerical approximation will get better. And eventually it should converge to the true, the result of the stochastic differential equation. So if we take the learning rate, so now let's think in terms of gradient descent, actual gradient descent. If we take the learning rate to 0, right, that's making this numerical approximation better. But we need, as we take the learning rate to 0, if we think of that as delta t, we need to take the number of steps to infinity. Okay, now, what about stochastic gradient descent? So I defined this thing in terms of total gradient descent. So that's well defined for the whole training set. But now what if we start doing mini batches or batch size 1, and we take the learning rate to 0? Will we still get, as we take the learning rate to 0, are we still going to get that same differential equation? Is it still going to be an approximation of that same differential equation, even with this noise in it? And the answer is yes. If you take in the limit as the learning rate goes to 0, what you can do is you can take a bunch of values of the parameter. So I'm thinking of this as we've got our parameter update like this, but now this is a stochastic estimate of the gradient. It's not the total gradient. So that's going to give us a sequence of values, but I'm going to divide this sequence of values into blocks that are of size square root of n. So what's happening is that the size of each block is going to infinity, right? Because n is going to infinity as delta t goes to 0, n is going to infinity. Each block is going to infinity, and the number of blocks is also going to infinity, right? So as each block goes to infinity, the update over that block is going to 0, right? Because it's a vanishingly small fraction of time. Since the number of blocks is going to infinity, this is a little teeny piece of a fixed amount of time. So the parameter value over that block is not changing significantly, but you're averaging together an arbitrarily large number of gradients. So within that block, the gradient is becoming exact. So it's becoming an arbitrarily large number of exact gradient updates. That's a real physicist argument. Is that compelling? No. Anyway, the answer is as eta goes to 0, if you hold eta constant at some very small value and look at the time evolution of your parameters, as eta goes to 0, that time evolution of the parameters approaches the gradient flow, the continuous gradient flow. Okay, I think maybe I'll do a little preview of stochastic differential equations. Maybe not. Are there any questions, do people make sense out of this enough to even ask a question? So if we think of total gradient descent as a numerical approximation of the differential equation, it seems intuitive that as that delta t goes to 0, the approximation, that's the numerical sequence of parameter values, will approach the smooth curve of the gradient flow. So the question is that also true for stochastic gradient descent? So that's what this slide is about. And it's arguing that for stochastic gradient descent, as the delta t goes to 0, it's also true that that sequence of values will approach the smooth differential equation value. And the reason for that is that even though the updates are stochastic, you can group the updates into 1 over root n groups. And since the size of that group is going to infinity, the update for the group is becoming exact, because you're averaging over an arbitrarily large set. So then you get a sequence of exact updates, an arbitrarily large sequence of exact updates. Okay, so next time, we're going to start talking about stochastic differential equations. And what's happening in a stochastic differential equation is we want to run at a finite temperature, right? The gradient flow is 0 temperature, right? It's noiseless. There's no noise in that differential equation. It's following a deterministic path. So it's like it's running your gradient descent at 0 temperature. Real SGD, we want to run at a finite temperature. Okay, but it turns out that mathematically, if you want to understand things and really, sometimes you get a better understanding by making a continuum model, making a continuous model, continuous time model. So a stochastic differential equation is a continuous time model of an MC-MC process at a finite temperature. And so intuitively, you've got continuous time. So Brownian motion, I don't know if you've encountered Brownian motion due to Einstein. It says that if you take a piece of pollen in water, it's jiggling. And if you look at a delta t, where it is over delta t is some random motion. But the delta t can be taken to be arbitrarily small. And you can actually think of it as a continuous process with random noise, and that's a stochastic differential equation. And by taking that limit, that continuous time limit, you can derive certain theorems. And there's something called Langevin dynamics that you'll encounter in a significant number of deep learning papers. It's based on this stochastic differential equation thing. And that's probably the sexiest mathematics in this class. Okay, so, exam tomorrow night. 5. Sorry. I was writing the exam and I threw in, I shouldn't even tell you that, I threw in a question on the transformer.
Is this supposed to take the entirety of the 3-hour time block?
I don't know. I have a hard time estimating these things. I believe it's significantly easier than last year's quizzes. Last year's quizzes, people were up against the time limit.
Isn't it in terms of being able to finish, but not the other difficulty?
And I'm not sure that they're easier. All right, and Pedro has office hours tomorrow. Yeah. Just take pictures of your pages and submit on Canvas. And I'll be on Piazza because inevitably there are lots of questions during the exam. So questions, you can ask things on Piazza. Okay.